This is actually figure 2, a graph representation of the different fields. We'll get into that in a minute. But let's continue with this point 1. And so that the point 1 splits between neuromorphic computing and neuro-inspired learning. So neuromorphic computing is a hardware implementation that moves us away from von Neumann architectures towards things that are more biologically inspired. So von Neumann architecture, of course, separates out memory and processing for very practical reasons, but that's not really maybe the way we want to build devices that are inspired by the brain, because that's not really the way the brain works. And so you can build these neuromorphic devices that are much different than the von Neumann architecture. And then neuro-inspired learning, which is where we have different types of algorithms and software that are inspired by the brain. They're not at all like the kinds of algorithms that we have for von Neumann architectures. If you know anything about how to, the different types of algorithmic challenges we have for, like parallel computing and for quantum computing, you know that like the algorithms for those paradigms look very different than sort of the serial von Neumann architecture algorithms that we may learn in like our computer science classes or something like that. So if we have like we have a certain a search algorithm that we build for a serial von Neumann architecture. If we want to parallelize that, it's going to look different. And if we put that on a quantum computer, it looks different still. So there are a lot of these neuro-inspired algorithmic opportunities to build new algorithms, build new sort of computational tools. So the second part of this categorization, so there was fields that do not involve living neural cells, and then 2 are fields that involve living neural cells. So this is where we want to kind of leverage the efficiency and adaptability of brain neural networks and integrate biological neurons with digital systems. So this, of course, is organoid intelligence and bioengineered intelligence. And so this is where you're using organoids or some sort of culture, cell culture, to build these systems that can process information and do this in a way that's similar to what in vivo nervous system does. So sometimes people are using brain slices for this, but other times they're using neural cultures. These BNNs can be integrated with computers to develop effective brain-computer interface systems.
There's a longer discussion that relates to some organoid intelligence and brain-computer interfaces. This is not getting us any closer to putting either putting organoids into brains or decoding. This isn't decoding a living brain either.
Right.
But these are my issues that I need to work through.
Yeah.
But I love this graph.
Yeah. So this is figure 2. Yeah.
This is cool, and I'd never thought about representing it this way, but it really it captures well the complex relationships.
Yeah, so this is where we have synthetic biology, cell and tissue engineering, neuroscience, computational biology, and so these are all the fields that kind of go into this enterprise.
Yeah.
And then all the kind of the tools that we have here, neural tissue culture, computational modeling, cognitive and systems neuroscience, machine learning, and then the next level are these kind of different approaches: neural tissue modeling, neuromorphic computing. Then you also have reservoir computing and feedback driven learning, and then synthetic biological intelligence and neurodigital twin model, and then NeuroAI.
There's a lot of acronyms to learn here.
Yeah, they throw a lot out there.
trying to define them for us. But as you go down, they start using their new acronyms.
Yeah. Where did that come from?
To make additional acronyms. Okay.
All right.